All right. Last one here for buffers. Reads a buffer is prepared that contains zero point 0.2 molar HA and 0.15 molar A minus. Now, of course, when you see this terminology, that's our acid and our base, respectively, right? It's acid and the base, respectively, okay? So we're telling you the concentration of the acid in the base form. We're told the initial pH of the solution is 3.35. And then we add some sodium hydroxide to the mix to kind of mess things up. We want to know what is the new pH. Now, we're not told what the pKa of this acid is, but we know from the HH equation that if I take the pKa and I add the log of this ratio on the right, I got to get my pH. So my first step here is to figure out some characteristics of my acid. I'm going to take my 3.35 pH and I'm going to add it to my pKa. Or I'm going to set it equal to my pKa, times the log of the ratio between the base and the acid concentrations, which of course is 0.15 molar divided by 0.2. Get those numbers from the problem. So it looks like to me that if I solve for this term over here, I got negative 0.1249. I get to add that to the pKa, and when I do, I need to generate the number 3.35. So if I do the math, algebra I guess you'd say, figure out what my pKa actually is, it looks like it's 3.474. So if I take that and I subtract 0.1249, indeed I get 3.35, okay? So I erase it a little bit. So I gotta rewrite that because I'm gonna need that pKa again eventually, and I just need to make some more space because I need to keep working this problem. It's gonna be pretty quantitative, isn't it? So my pH is a little bit below the pKa of 3.74. That makes sense because it looks like I've got a little bit more of my acid form present than I do my base form. Alright, so where do I go from here? I now know my pKa. Actually, I should put it right here, shouldn't I? That's a very logical place for it. 3.474, since it won't change anymore throughout this problem because it's governed by what the acid is. Alright, so now I'm to this point, and I'm told that I take some of this buffer, specifically a volume of what, half a liter? Yes, 0.5 liters of my buffer, and I add to that 0.0015 mole of some sodium hydroxide, which hopefully we identify as a strong base. How do things change? Well, here it's a complicated problem, it's quantitative, but before we do any quantitation, you have to write the chemical equation for change. How are things going to change? Well, if I add a strong base such as sodium hydroxide, I know that it can react with my acid component of my buffering pair. That's my HA. And in the process, I'm going to deprotonate the HA to make the A minus, and I'm also going to make water. That neutralizes the addition of the strong base. But here's where I need to get real quantitative. So I have my reaction, but now I need to write my RICF inventory type approach to figure out how things change from the beginning to the end of this reaction. So here's where I got to get quantitative. And when I'm treating my reaction as a one-way street, I always like to work the problem in terms of number of moles of substances present. So I need to multiply my molarity times volume for the substances to figure out the initial quantities involved. Now, I know how much NaOH was given to me. That many moles, 0.0015. But I don't yet know how many moles of HA was present in my buffered system. However, I do know the volume of the buffer was half a liter. Do I know the molarity of my HA? Oh, if looking back to the problem, I do. It's 0.2. So what would stop me from taking 0.2 and multiplying by 0.5? That informs me that I've got 0.1 mole of my acid present. In a similar way, can I figure out how much of my A- form, my base, is present? Absolutely. I still got half a liter of my solution. But here, the molarity is not 0.2, it's 0.15 for my base. So I need to do 0.15 times 0.5, which yields 0.075 moles. And remember, I usually don't track water. So this is my starting point, all right, my initial. Now I got to predict my chemical change. Which direction will the reaction shift? Well, if we're taking a strong base and reacting with the weak acid, we're going to go as far to the right as we possibly can. 100% to the right. So we're going to use up some HA, we're going to use up some OH minus, and we're going to make some of this. But of course the key point here is how much of each we make. We said since we can make the assumption of going 100% to the right, it becomes a limiting reagent problem. And since it's a one-to-one stoichiometry, it's clear to see that we're going to run out of the OH first. I can only use up 0.0015 moles of that, and once I do, it's all gone. But in the process, I also consume 0.0015 moles of my HA, and I make 0.0015 moles of my A- form. So if I take 0.1 mole and I subtract 0.0015, I find that I've got 0.0985 moles remaining. And likewise, if I take 0.075 mole and I add 0.0015, I now have 0.0765 mole of the A- form. So what we did here is we considered the chemistry and we found how things changed from the initial quantities. We worked our inventory in terms of moles, assuming the reaction moved to the right with 100% completion. We're always going to make that assumption as long as one of the pairs in our reaction, the acid or the base, is a strong acid or strong base. We come to that point in the problem now, which is always my favorite point, right? Because you get to talk to yourself. You have to ask yourself, what do I have here? What controls the pH? And in such cases, the first thing that you usually want to ask yourself is, have I exceeded my buffer capacity, or do I still have a buffer? Do we still have a mixture of a weak acid or base or not? We do have a mixture. We've got both. Still, we have not exceeded our capacity. So we still have a buffer present. And if we still have a buffer, we can use our friend, the Henderson-Hasselbalch equation again, to help us compute the pH of a buffer. As long as the buffer is present, as long as you've got the weak acid and the conjugate base in solution, you can use your HH equation. It's very, very user-friendly, isn't it? Alright, so here we're going to solve for the new pH. We said earlier that this particular acid has a pKa of 3.474. That's not going to change. It's governed by what the acid actually is. And now all I need to do is find the concentration of my base and my acid. Remember, the A- one is what? The base. And the HA is the acid. Now when I plug into the Henderson-Hasselbalch equation, I'm really formally supposed to plug in molarities. So, I mean, I guess I would want to recompute that to be sort of a purist with this, right? It's kind of a shortcut, but if we're going to recompute it, we probably should. So I'm going to clear off some space here on the top. What's my molarity of my HA after the reaction's complete? Well, it's moles divided by liters, isn't it? I did my RICF table. I figured out that I had 0.0985 moles of that present. Now, do I know how many liters are present here? I don't remember discussing that completely. It looks like I've got 0.5 liters to start with, and then I added some sodium hydroxide to it. But you know what? It doesn't really tell me the volume of that I added, does it? So in such cases, I guess we can just assume it's 0. In some cases, maybe the problem tells you that you add 5 milliliters, and in that case, you have to add that back into the total, right? But here, since we're not told that, I'm just going to say that we have 0.5 liters of volume, that it's unchanged, that we added the sodium hydroxide with no change in the total volume. And if I did that, then I can do 0.0985 divided by 0.5, and that's going to give me 0.197 for my molarity of my HA. Now remember, the acid goes in the denominator. It needs to go down on the bottom. And I'm going to do a real similar calculation now for my base. I'm going to compute my A minus concentration. Still have half a liter of volume, but now my A minus is what? 0.765 moles. So now I'm going to take the 0.0765 divided by 0.5. It's going to be 0 there too. And you get 0.153 mole per liter for that one. So 0.153. And now we can start doing the math. So I take that 0.153, I divide it by 0.197. And when I do that, this ratio becomes 0.776. Okay. Now I'm going to take the negative log of 0.776. And when I did that, on my calculator, I get 0.1098. So it seems like all I need to do now is to take that number. Ooh, that's, I took the negative log on accident. So this actually should be a negative sign. You get negative 0.1098. So what I need to do is take that number and add it to 3.474. Oops, I did the wrong math on my calculator. Okay, let me do it again. 3.474 minus a 0.1098. I get 3.36. And that should be my final answer. Okay, so let's just rehash. This buffer started 3.35 pH. We used that to find the pKa. We then added a very small amount of a strong base, sodium hydroxide. Composition of the solution changed. The reason being is because I converted some of my acid to my conjugate base. I increased the amount of conjugate base present, and I decreased the amount of the acid present, didn't I? That affected my ratio term in my Henderson-Hasselbalch equation. And because of that, the pH changed, and it went up ever so slightly. Not very much. Reason being, I didn't add very much sodium hydroxide. but the pH did experience a small increase. And this is how you generally work these problems, where you have a small change in pH after the addition of a strong acid or base to a buffered solution. You always basically consider what you add, and then you start with a chemical equation that explains what's going to happen in the buffered solution. And that's why those equations are so crucial that you master, because you got to get that equation or you're going to be lost, right? So practice writing those equations for the addition of a strong acid or base to a buffered solution. And once you master that, I think everybody can pretty much do the mathematical work, right? As long as we don't make a simple error. All right, well, that's this one.